Okay, so what we're going to talk about is temperature changes. So you have a graph, just an axis. On this side of the axis, we're going to have heat. Heat we denoted by the letter Q, which is literally like a fire. Just heat coming into, in this case, ice. Water is going to start at, let's say, minus 10 degrees C. The water in your freezer is about 0 to 2 degrees F. You can check. There's usually a digital number that will tell you, hey, this is what your freezer is at. You want to be not at 32, but you want to be way below freezing, because although we don't realize it sometimes, ice has different temperatures. It can go all the way to absolute 0, right? Which will be 0 Kelvin. I don't think we've ever reached that, but that's potentially what could happen. So ice, where you realize it or not, has vibrating molecules, and they are slower and slower and slower the more, the colder it is. So let's say we start at minus 10, then I like the metric system because it has it that it actually freezes at 0. At that point, it's going to go a transition and it's going to turn into liquid. So we're going to start with the ice, which is these beautiful crystals. These are not beautiful crystals, but that's what we recognize as ice. That's a cube of ice. And then the ice is going to be gaining some energy. And when we go through this is called sensible heat. Sensible heat. Why? Because the temperature is changing. I'm adding heat, and the temperature is going from minus 10, minus 9, minus 8, 7, 6, 5, 4, 3, 2, 1, 0. At that point, I still have ice. I can have ice at 0 degrees, but if I add any more heat to it, so if I continue to add heat, to put like a fire, to put my hand, is going to continue giving it energy. And the ice is going to turn into liquid water. Eventually all the ice, so you have here, you're gonna have a water-ice mixture. So you're gonna have ice in water until all of it turns into water, and the heat, what this heat is doing is loosening the bonds. So we start with ice, which is fairly rigid, right? They're vibrating, the molecules are vibrating, but it's still fairly rigid in these shapes. And then we start adding heat, and the rigid bonds start loosening and loosening and loosening until it can't have enough energy to flow and behave like liquid water. Because we don't see a temperature change, we call this latent heat. So this one is called latent heat, which literally means hidden heat, because we don't observe a change in temperature. But once all the water turn into a liquid, then we can go back to our sensible heat, the one that makes more sense. And we get into the sensible heat all the way, so the water will continue to gain energy and absorb it until it gets to about 100 degrees C or 212 Fahrenheit. At that point, we have still liquid water, but this liquid water is going to, if it gains any more energy, it's going to start turning into a vapor. So we're going to have a mixture of water and vapor, and water as a vapor. So it's going to be a mixture of water and water as a vapor until it all becomes a vapor. And then it's going to start again its path, and then it's going to start increasing in temperature until we can get something called superheated steam. And that is steam, and I need to remember to set it up in class. That steam can actually burn paper. And we have a little device that we can show you how it works, the superheated steam, and it's gonna go on and on. So what I want us to know is not get into a lot of detail. What we're doing with these presentations that you're having is not teach a topic, right? We're not teaching the topic. We are trying to get our feet wet, to get familiar with the concepts, and to start understanding, so when we actually cover this topic, it won't be from zero. We'll be at step 2 or 3, right? So hopefully it'll help us in understanding. I thought I would do it in one class. I think it's gonna take 2 or 3 classes before we actually get to finishing the introduction to these topics, which is okay if it works. So we have ice at 0. The molecules vibrate more and more and more until, at -10 until they get to 0. Then they loosen until they get to water at 0. Then they start, the heat that continues to be added is going to warm it up, increase the average kinetic energy until it becomes water at 100 degrees C. Then we're going to start loosening those bonds. This side is so much larger. So this is called the latent heat of melting, because we're literally melting. And this is called the latent heat of evaporation, because that's what's happening. As we go up, it's all an endothermic reaction. Warming up, melting is endothermic, warming up, evaporating is endothermic, and going all the way up is all endothermic. If you go up, it's endothermic. And we call that positive heat. Anytime you require energy to melt, you require energy to evaporate, it's called a positive energy or a positive heat. But we can also go down. Now, if we have water at 100 degrees C, you will never, if you add heat and heat and heat, you're just gonna evaporate it. If I boil water for 300 years, just have water boiling, it will never be greater than 100 degrees C. It'll just give the energy to the vapor and come out. So literally the evaporation is cooling off the water that stays behind, because it takes the extra energy with it. They call this evaporative cooling. When this happens, something cools off. So the water will get hotter, but it won't be hotter because the steam takes it. Evaporative cooling. And you have all experienced evaporative cooling as well, because water not only evaporates when it reaches 100 degrees, sometimes you will have some water. Let's say you just went to the pool, or you were sweating after a game, so you've got water all over your body, but your body's hot, right? So your body will actually give it enough energy for that little bit of water to evaporate. And when the water evaporates, how do you feel? Maximo. What? He was a little distracted, that's why I asked.
When water evaporates, how do I feel?
Yes, because it's evaporating in your body.
Oh, in my body?
Yes.
Not feeling.
Cool. Imagine that if I gave you, he's like, well, what's that? Now imagine, or happy, if I gave you alcohol and I put alcohol and you did like this to your hand to help it evaporate faster, it feels really cool, right? And that's if you get out of a pool and you do not want to get too cold, what do? You dry yourself off the best way you can. That way you don't get as cold. If you leave the water and you stay out of the pool and you stay like that, or if I walk out of the swimming pool all wet, I'm going to be really cold, especially on these really cold days, right? Because as that water is evaporating, you will get really, really cold. So evaporative cooling, this latent heat of evaporation, the fact that when something goes from a liquid to a vapor, it cools something, believe it or not, is what cools your the air in here that we have. It's how refrigeration works, how an air conditioner works. It works literally on this principle. When they have a refrigerant, when that refrigerant goes from a liquid to a vapor, it cools all the air that goes by it. And that's how we cool this building. And it also applies to how your freezer works. You have a refrigerant in your freezer that is turning into a vapor. And when it does that, it cools it. Somebody needs to be cooled, literally. Maybe I'll cool you up a little bit and then you stop closing your eyes. So, now, does this make sense? This is all endothermic. It all requires energy, and you have the evaporative cooling. It's used in this is used so much. It's used in hurricanes. Evaporative latent heat of vaporization is actually the fuel for what a hurricane happens. It has a million applications. Now, I said that going up was endothermic. Well, going down is exo. So if I have a steam, for the steam to turn into liquid water, is going to have to get rid of heat. That's exothermic. Then it's exothermic to have to cool here. Now the one that people get wrong is water, like you are all mostly made out of water. If you were to freeze, right, you have to give off heat. So that's exothermic. For something to go from water to frozen is exothermic. Most kids think that it's not because it feels so cold, but if for something that to be frozen, you have to lose your heat for you to freeze. So that's exothermic. And as the ice goes from 0 to below, it's also exothermic. So we have sensible heat. Is the heat that we can sense. This is also sensible because we can sense a change in temperature, and this is also sensible. That's heat and that's temperature.